So in the first part of this video lecture, which is intended to prove this theorem, Radon Nikodým Theorem, what we saw was the definition of absolute continuity. That is, we say that nu is absolutely continuous with respect to mu if every set that has measure 0 for mu also has nu measure 0 as well. And then we saw here an example of a function that was absolutely continuous with respect to another, or a measure that was absolutely continuous with respect to another. And then we were discussing the question. We saw that whenever a measure nu has a density with respect to a measure mu, this would imply immediately that it is absolutely continuous with respect to the mu. And then we're asking the reverse question. If it is absolutely continuous, does the derivative exist? And this is what Radon Nikodým theorem says. It says nu is absolutely continuous with respect to mu, and the theorem holds when two measures are sigma finite. It doesn't say anything about what happens if one of them is not sigma finite. Now, given two sigma finite measures on a measurable space, so one of them is absolutely continuous with respect to the other if and only if there is a density. There is a density relating the measure on the left to the measure on the right. Okay, if and only if, of course, one direction is easy, as we discussed already towards the end of the first part of this video lecture, but it is this implication which is highly non-trivial. We're not going to see the proof of this theorem. We're going to just accept it. It is there are references in the lecture notes for those who want to see the proof in details. What we're going to do in this unit is to explore corollaries of this theorem and crucial consequences that it has for probability theory. Let us conclude with a remark about random variables. We say that a random variable is absolutely continuous if its distribution px, if px is absolutely continuous with respect to the Lebesgue measure, which means every Borel set that has Lebesgue measure 0 also has px 0, which means for every B Borel set, if the Lebesgue measure of B is 0, then the probability that x is in B is 0. So this is the definition of x being absolutely continuous. And from the previous theorem, which is Radon Nikodým theorem, if a random variable has this property, so if a random variable is absolutely continuous, if it has this property here, then it must have a density. So in the next video lecture, we're going to explore further this notion of when random variables are continuous, absolutely continuous, etc. And after that, in the last video lecture, we're going to show a rather surprising application of Radon Nikodým theorem, which is the existence of conditional expectations.